You're the boss.
I'm the boss, but I obey the schedule. Let's see, what do I have?
Yeah, we're on break. And then we have tutorials.
We're on break until 3 o'clock, and then we will have our tutorial. For those of you who are interested, I should give you the code again. Withered Vampires 2. Let me do the screen share. Let's see. All right, so if anybody wants to set up for the tutorial early, you can create your name and log in, use your login name and password using that code, Withered Vampire 2. No, that's actually randomly generated. It could be a book title, Withered Vampire 2.
It was the third quote.
Yes. Don't make a one to start.
That's right.
That's to the.
It does. I agree. It does. Withered Vampire 2.
See your students with romance novels.
Withered Vampire 2. It's totally random.
Yeah.
You won't even find it.
Especially.
It's one of the few sitcoms I think sit through. I don't know, I have trouble with sitcoms. Oh, with Austin. Yes. Thanks, yeah.
So, it's
It's the same version.
like,
But it's
so, primary. That bill, back.
easy cable. Oh, I'll put that up there soon. Yeah. We do that.
That's road. But it's set up from back. This.
Coming from the club.
Yeah, derivation. That'll the main one is make an exception. The fee is, the loss is different.
Yeah, I have to take that out.
Yeah. But it's like the coming answer. Yeah, you'll have to. Great.
Yeah, I did that one with.
Yeah.
Not by setting up projects. Fresh well. By little bit, the data, and then we look possibly this data set up, and then sets up some data. But then they kind of stop. So they found the diverse velocity and smack with some pressing smack. Next that as well. Yep. Sometimes when set up problems, usually does we just one better tap that out. Noise. Everyone has like that. Not quite yet. It's still different. Quite enough.
An unknown character. Error. Right. Minimized on me. Share. All right. So. Let's see, how many people have we got online? Participants 9. We've got 9 participants online. And we've got more than 9 in the room. So somebody was kind enough to broadcast the code and the server name to everybody in the room. If you have not done so, please create your login. In order to do so, you can visit the URL that's given in the chat. And that withered vampires 2 goes into the code at the bottom, but you can invent your own login name and password. And once you've done that, you should get an account that's pre-populated with all the tutorial notebooks. In case you have already started experimenting with the notebooks, please note that right before this talk, I recopied all the notebooks to your home directory. So they might have, if you had done something, it might have gotten overwritten or changed. And sorry about that. It's a one of many weird technical problems that I'm sure we'll face together. So while you're in the process of getting your login set up, if you have not already done so, is there anybody here who is unfamiliar with Jupyter Notebooks? Is there anybody online who is unfamiliar with Jupyter Notebooks? Speak up now or forever hold your peace. You know what? This is the first time I haven't gotten a bunch of hands at this point. Okay, so proceeding with your expertise, knowing you're experts in Jupyter Notebooks, let's take a look at what we've got. Now, most of the stuff in prerequisites isn't relevant to this particular session, but it will be relevant if you want to set up the Einstein Toolkit on your laptop directly. We don't want to set up the Einstein Toolkit on people's laptops directly as part of this tutorial, because too many things can go wrong, and you know, it just depends on all the little details of how your laptop is set up, and it's something that we could potentially fight with for hours depending on what your laptop is like. On the tutorial server, we have a controlled environment. We know exactly what things are installed and where and so on, and so it's much easier. So these instructions are for you to look at home if you want to run directly on your laptop or cluster. Scrolling past them, we have this magic cell, and it's just got a couple of definitions that we like to use within the notebook itself. In particular, it has this %bash thing that it sets up to work a certain way, and environment variables it sets and so on. The ET setup is just a place to standardize all those little settings. So just execute that cell. Now, the next thing to notice about the Einstein Toolkit, we're going to teach you how to download and install the full software package. And it is way too much, even for this tutorial server, if we were to have everybody in the room simultaneously download and install the thing. It would overload the network, right? If everybody's suddenly downloading all that data over the network, and it would cause other problems as well. So we have what's called an optimized build experience, where we have a pre-built Cactus binary in the tar file. And by running this cell, what you're going to do is extract this. And it's going to make sure that you have all the files in all the correct locations with all the correct file permissions and modification times and so on, so that your build, so you won't have to rebuild hardly anything. And all the steps that follow will do mostly nothing, except they should work the same way with or without untarring this thing. They should give you the same result at the end, but it should just take far less time. So this step is going to take a little while, partly because we're now overloading the file system, right? Because everybody is doing this same thing, and it's overwriting everything. Now, if at any point during this tutorial you screw up your installation, you modify some file or you break something, you can always rerun this particular cell and restore everything. If you right-click on your cell, there is enable scrolling for outputs. You can do that, and that will reduce the number of outputs that you see in that given cell. By default, Jupyter Lab, which is what we're using here, will just not scroll. It will just let that take it however much space. So that's a thing that you might want to do. All right, so this thing is still unpacking. Let's see. So we'll give it a few more minutes. Now, the next thing that we're going to talk about, I'll just start talking about the next thing. Make sure we're in the correct directory. Now, the way Cactus is distributed, the idea was we didn't want, Paul Walker and John Masseau, when they created this, didn't want to be a silo where, they kept and controlled everything and people had to go through them, right? Because that would not have built the kind of community that they wanted to build. So what they did is we created this Perl script called get components. And the idea is we have this get components reads this thing called a thorn list, and it checks out a bunch of different software repositories from a bunch of different locations. So the Einstein toolkit isn't centralized. It comes from multiple different repositories in different places. Now, if we were building this thing today, I guess we would use Git submodules to do it, and everything would be based on Git. At the time this was built, Git didn't even exist, much less Git submodules. And so what we had instead was sort of a bunch of different popular build systems. There was RCS and Subversion and Mercurial and a couple other weird things around there. And we tried to support them all. So you could have your repository come from any of these kinds of places. And that was, so this is what we built, and it still works. Mine seems to still be running. Has anybody's untar finished? Nobody's untar has finished. Excellent. All right. It's at 97%. There we go. Finished. Done. I just had to wait a few more seconds. All right. So the first step here is we're going to curl the latest get components script, change its permissions so that it runs. And now we're going to tell get components to check out our thorn list. Now the thorn list that we're going to use is stored under the ET user Einstein-workshop-2024.th. In comments, I have the full checkout for the 2023-11 release. We have a couple of differences in the release that we're using, in the thorn list we're using here from the official release to support the Asterix tutorials later on. When you go to run this, you should see something similar to this. It's going to check out. Why is it checking out space-time? Interesting. Okay. All right, so the next thing we're going to do is configure and build our Cactus simulation. And what we use for this is a tool called SimFactory. SimFactory is a tool that's written in Python. And one of its primary purposes is to insulate us from the variations of the machine. So where this is most noticeable is when you're compiling, right? Trying to get the right balance of which MPI to use, which fast Fourier transform to use, which HDF5 library to use, and all this other stuff, which compilation flags do I want, and so on. These can all be somewhat difficult things to work out on a new cluster, and sometimes involve a lot of trial and error. And but once you figure out all these details, you can capture them with SimFactory and make them available to others. And we try to keep SimFactory up to date for the major supercomputers that we use. All right, so the first thing you need to do if you're going to use SimFactory is you invoke the setup silent command, where SimFactory does an initial configuration of itself. All right, and it just keeps track of what my email address and who I am, and whether I have an allocation or not at the moment. All right. The next thing I'm going to do is build. Now, in this case, the build should do very little. And you notice there is a magic %% slurm. That was something I invented for the purpose of doing these notebooks. So what that will do is it'll throw the build process into the slurm queue and potentially distribute the work away from the web server and onto multiple nodes. And it should result in things just running faster. And it produces a lot of output even when it's doing nothing. That is, the Cactus build system does. It's got a few things it always builds no matter what. And so it's not quite done yet. If you were trying to build the full Cactus system, it would be, as I said, we would all be sitting here until tomorrow because we would overload the disk system and there'd be so much for it to do. It's running slightly slower than I would expect. But as you can imagine, once you take, you can get any system working perfectly for one person, and then you put it into a full classroom, and yeah, it's slower. All right. So any questions on anything so far? All right. So once we get this working, the first thing that we're going to want to do is we're going to run a simple parameter file. And that's going to be, shoot. Oh no, this is fine. This is going to be a part file for hello-world.par, and its contents are listed for you right there. It just says active thorns equal hello world. It's just going to load that one module and run it. And I'm going to click Shift Enter on this and on this next command. So SimFactory, when it runs simulations, it's got two. Yes.
All we've done. It's just there.
Yes, we've downloaded the code and we've compiled it. Right, and then we set up SimFactory, which is the other one thing we did. And let's see how I'm going. Oh, looks like I'm making a lot of progress. Still checking things. Compiling a few random. You know what? Whenever we do this, some random weird thing goes wrong. Why is it doing compilation? The last time I ran this, it didn't. But this time, okay. So strange. Just a few random files here and there. Huh. All right.
All the part files need active thorn.
That is the minimal par file, yes. Well, that's what this one has, Roland. Okay, it won't do anything.
So.
Sure, okay, you can have an empty one that does nothing, I guess. All right. But in reality, having an empty one and having one that just says hello world isn't particularly useful. All right, so it's almost done. Formalin is a special thorn. We don't technically need it, and it does waste some resources when it runs in terms of compile time and so on. But what formalin is useful for is when formalin runs, it captures your source code and every detail about your build, so that later on, if you want to find out what you did, right, it's preserved. Because you might have made modifications to the source code in small ways when you compiled it for the machine or for some other purpose and forgotten that you did it. This is not an unusual situation. And formalin helps you preserve everything that you did for the purpose of recreating runs. When I was a grad student, we had some black hole collision that we did, a head-on black hole collision. Back then, the 2D calculation was state of the art. And it got on the cover of Science, and we had this nice visualization of gravitational waves on the cover of Science. A year later, we had no idea how we did that. I mean, so you need tools like formalin to help prevent that sort of situation. Right? Reproducibility of software was something people hadn't really started to think about too hard back then. But we do think about it now. All right, it's still pondering. Ah, look at that. Look at that, it's linking. It's always great when you can get excited about the most basic things. My code is linking. All right, so it's going to finish linking. It's going to run some other, it's going to compile some other small programs, and then it will be done. And then we're going to run the Hello World program. So let me talk about SimFactory a little more. So SimFactory, you see, has, when we invoke it, we have this create, run. So create and run are two distinct steps in SimFactory, right? So I can create a simulation, which, tells it which parameter file I want to use and some other information potentially. And it just creates a placeholder for doing simulations there. And then I can either use run if I want the program to run in the foreground, or submit if I want it to run in the background. In this case, I've compiled, I've done create and run all in one step. But in practice, I might separate them. And the advantage to separating them is that I might want to do run more than one time. So if I do that, it will pick up from a checkpoint file. It potentially can pick up from a checkpoint file and continue the simulation, depending on whether I've configured things properly for that. Okay, right. So I should be almost done. We will be capturing load metrics on this to see what's going on. We always do. Still linking. Any questions about any of these pieces so far? So one of the things that SimFactory isolates you from, right, in addition to isolating you from the build details that you need to get everything to compile perfectly, is how to run things. In principle, SimFactory should be able to give you the same commands to run your code, whether you're on a laptop with no job manager, or if you're on Slurm or Load Leveler or SunGrid Engine. Because each of these machines, or Torque Moab, all these different job management systems work slightly differently, and you might not want to keep track of all the details of each one. Look at that, all done. Building utilities. Now it's got to build the utilities, and then it should run my Hello World program for me. Has anybody gotten Hello World to run yet? Are you behind me? One person? Okay. So we all proceed at slightly different paces, of course, depending on the way the jobs happen to fit into the system. And looks like I'm building all my utilities. Done. And voila, my job runs. And somewhere in here. Here we go. There's a schedule tree and hello world, hello world, hello world, hello. Okay. How many people have gotten to this point? Still just one, two? All right. You're going to get there shortly. Okay, so that's the first Cactus program. That's the most simple step. Any programming language or framework or whatever you want to use, the first thing you need to do is you need to know how to run Hello World. And so we have accomplished that. That's no small thing. It is a small thing, but it's also not a small thing. Okay, so the next thing we want to do is jump right from doing Hello World to running a TOV star. So a TOV star, so I skipped some cells. Yes. No, you're going to specify that elsewhere. That doesn't go in the par file, the number of cores and everything. So I failed to run these two cells, and let me just run them. So I'm going to create and I'm going to submit. Yeah, okay, overwriting. Okay, so I've created and submitted these two things. And now I'm going to list the simulation. So SimFactory is going to show me what's running. And it says that the TOV simulation is active and running as job ID 40. I can now do show output. And it's going to start running and showing me output as it does this TOV simulation. And it's off to the races. So this will now run. This is already well on its way. Now, this particular step, unfortunately, will take 20 minutes. I think what we've said above here is, these are my glasses with the weak frames on them, fall off my nose. Yeah, we said up here that our maximum wall time would be 20 minutes. And we do this because, this code can run for a very long time, especially when the machine is loaded. And 20 minutes is kind of like a balance where we get something substantial and we still are able to talk about other things that are going on. But in principle, you could take this home and you could run it for longer if you so chose. Yes?
So why, what happened if you don't specify cores?
So it has certain defaults that it assumes, right? And the defaults are going to be specific to the configuration file for the machine. In this case, what I'm saying is I want to run two. So when I say 2 cores and num threads equal 1, that means I'm going to run 2 MPI processes, and each MPI process is going to get 1 thread. If I wanted to run 1 MPI process with 2 threads, I would have said cores equal 2, num threads equal 2. So if you want the number of MPI processes, it's going to be cores divided by number of threads. So that's just basically the way that's basically the way you submit things to SimFactory. Let's check on how it's progressing. Yes. No. It's all experimenting. It's different on every machine. I want to say that a lot of the time you only want a few threads per core, like 2 to 4 or something like that, and then let MPI handle the rest of the parallelism. But this general rule should not be taken as gospel. I mean, you just have to test. Yeah, it depends on the node. Yeah, there's so many details it depends on, and so many of them are just things you can't figure out. You just have to experiment if you really want to know. I mean, how many pneumo domains does the machine have? What is this cache? Blah, 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 blah. So many things. Okay. It's almost infinitely complicated. Anyway, while that's running, what I'd like to do is take a little look at the par file. And I don't know that I want to talk about every single thing that's in here, but just some subsection of things. So active thorns, time and method of lines. So method of lines is going to be our time integration method, right? And if you want to, you can take a look at these par files. Let me do that interactively. So you can open a terminal, right? And you can go into your Cactus directory and repos Einstein, what is it? Utils? No, Einstein numerical. No, it isn't. It's Mal, Cactus numerical? Yeah, okay. So if you want to look at the mol par file, right, you can see all the different time integration methods that are available to you. You have iterative Crank-Nicholson and Euler. If Euler is what you really want, we have various types of RK2 and RK3 and RK 4.5 and RK 6.5. There's an RK 8. There's a wide variety of things in here. I think that RK4 is what most people use, but I just, there are other possibilities, and you can choose different things if your simulation needs it. So that's what MOL is for, and this is how you find, the various. So I would encourage you to look at the parameter files and the documentation there when you see strange things in a par file. Okay, so that's the first thing. And then we have coord base and cart grid 3D. These are the two things we're going to use to define our grid. So we've got a couple of things that we set here, but the thing to notice is xmin, ymin, zmin, xmax, ymax, zmax, and dx, dy, dz. These, I hope, are fairly intuitive names for how you set up the grid. There's some other stuff, as I say, around here, which you might want to look up. So very few people who run Einstein Toolkit start with an empty par file and just start typing things, right? What you typically do is you borrow a par file and you start editing. Because there's so many things that you can potentially set and can potentially need to set. Figuring it out from scratch is just difficult. So TOV star is a nice thing to start with because it's a nice, simple problem, as simple as you can get and still be sort of a real problem. And anyway, so that's how you set up your grid. And then you can give carpet instructions on mesh refinement. Now, in this case, what we want to do is we want to set up a mesh refinement box around our TOV star. We're going to only have one level of refinement because we don't want the computation to take forever. This is going to be an under-resolved TOV star. If you want to take this notebook and what you've learned here and beef up the processing and the grid, and the grid size and so on, you can. But what we're going to do is we're going to have one refinement center, and we're going to have two refinement levels. So we'll have a coarse grid and a finer grid, and the radius of the refined grid will be 12. That's the radius of a rectangle, not a sphere. So we also specify the boundary sizes around the grid. Remember, we talked about ghost zones before, and we have ghost zones and we have boundary zones. This is the number of boundary zones that we have. Typically, we want that to match the number of ghost zones. There is a shift that we do to the origins. That's just sort of getting the coordinates in a certain way that we want them. Active Thorne's reflection symmetry. So what we're going to do in this case is, we're already doing something silly here, right? We're taking a spherically symmetric problem and we're evolving it in full 3D using adaptive mesh refinement, okay? And obviously it would be much more computationally efficient to evolve it in 1D, but the point of doing it this way is that we can test all our 3D infrastructure and make sure it's not messing things up. So, but even though we're running in full 3D, we're taking advantage of spherical symmetry in that we're only evolving one octant. The other 7 pieces of this simulation are just assumed to be identically the same as ours. And so we specify this reflection symmetry to make that clear. So let's see, spatial order 4, ADM macro spatial order 4, we're going to use 4th order differencing. Poisoning is something that you can do for checking, for error checking. It potentially slows your calculation down for a bit. Does somebody we have an extra bottle of water. I have this rule that whenever you go to speak in front of a room, you should always have a drink with you. And I did not obey my rule. And now my throat is scratchy. Yeah, would you please? All right. Okay, so poisoning. So poisoning is a NaN, a so-called not a number value, and we introduce these onto grids when they're uninitialized. And this helps us catch problems where we don't initialize things properly. It can also catch things when our numerics go astray. Max refinement levels. So this is the maximum possible number of refinement levels we could pick. And in this case, we've only picked 2 to actually run, but it's got space potentially for 10. And when it does this, each step of the course grid is going to be 2 to the 9th is in terms of internal steps. Ghost size 3, that matches the boundary size, which is what you generally want to do. We also specify a prolongation order in space and time. So when you do adaptive mesh refinement, there are basically 2 choices you can make about how the refinement is done. You can subcycle in time or not subcycle in time. What that means is, if I'm subcycling in time, that means for every step, I take 2 steps on the fine grid for every 1 step I take on the coarse grid. And that creates certain complications, right? When I want to do the synchronization, I now, on the fine grid from the middle, I potentially have to interpolate the data from other time steps. And my rescue is coming. Yes, I have a water bottle.
I figure you're a two-fisted drinker.
All right, I thought one was for you.
No.
All right. So we need to fill in those boundary zones on the fine grid in between steps of the coarse grid, and that's what we do prolongation for. Any questions? Yes. No. No, you can just sort of put things in any order and jumble them around. In principle, you can set something down here and then use it up here, and so on. It's supposed to be order free. Any other questions? By the way, the par file supports a lot of basic math. You can do like multiplication and division and maximum and minimum, and you can use other parameters to calculate, one parameter to calculate another, and so on. I do not believe that it is Turing complete, but it does allow you some basic functionality. Okay, the next thing is time DT fact. So I don't know how many of you are familiar with Courant instability, but this is a problem that you can have, right? For your numerical method, if you take too big a time step for the grid that you have, your code becomes unstable. High frequency noise appears, and in a short period of time, you are left with nothing but nans. Like one grid step is going to be 10 to the 60th, and the next grid cell over will be minus 10 to the 60th, and then it'll be plus 10 to the 59th and minus 10 to the 59th. So every other grid cell, you get a wild swing in value. And what happens is, if you take too big a time step, you get some small difference from one time step to another, and it gets magnified with each time step. And the cure for that is to keep the time steps small. There are also, so you saw that list of numerical methods, right? RK4 is stable if you take the right size time step. But if you take, say, Euler method, it's going to be unstable no matter what time step you take. It's just if you take a smaller one, it'll last a little longer, but it's still unstable. And the same is true for RK2. But once you get to the higher order methods, for various reasons, it becomes possible to have them be stable. And in this method, we are using RK4, and you need to give it the right number of intermediate steps and scratch levels. Some of this is black magic, sorry. And then we have our NAND checker, which is going to periodically which is periodically going to check for nans and kill the calculation if it finds them, because once they've appeared there, your solution is no good anyway. EOS Omni and GR Hydro. So this is a neutron star, which means it's using hydrodynamics, and it needs all the different things that go along with that. You have to specify your equation of state, your reconstruction methods, what to do if you've got discontinuities, and so on. In this case, let's see. Then other active thorns, generic FD, new rad. So new rad is going to specify an outbound radiative boundary condition. And what that should do is if I have waves propagating off the grid, they should propagate off the grid. There shouldn't be any reflection. It's a tricky thing to get right. And you can probably never do it perfectly, but it's something you want to strive for. Let's see, how are we doing on our simulation? I'm up to 171520. Anybody beating me? So, all right. So that just takes a while. All right, other parameters for the TOV solver. We need to specify the initial central density, the K and the gamma for the equation of state, and some other hydro parameters. IO outdoor equals $par file. So this tells you what the name of the output directory should be that all the output files should go in. And almost always people want it to match the same name as the par file. So in almost every par file that you'll ever see, you'll see this particular line. And maybe it should just become the default and you shouldn't have to put it there. Here's another option that you can specify for IO, and that's the out mode, whether we want one file or one file per process. One file per process is going to be more efficient because it means you don't have to route things through the processor 0. But it's inconvenient in other ways, and we're not going to deal with that complexity here. So we're going to use one file. In this case, there's some screen output. We're going to output every 512. We're going to output some information variables, the maximum of these quantities, physical time and maximum of value of rho. You can do various other kinds of output as well. So all of these things follow a similar pattern. So we can output the scalar variables with a maximum. You can put the fully qualified name with thorn and variable name. And then in curly brackets, you can put some kind of, whether you want reductions or, what reductions you want, norm 1, norm 2 maximum, and so on, infinity norm, and so on. It depends on what you want and what you need. And you can put out, you can output 1D information. So you can find, say, the value of rho and the pressure and epsilon and so forth across like the x-axis, the y-axis, diagonal line across all 3 axes, and so on. You can choose for HDF5 output, the binary output instead of the ASCII. You can output buffer points or not. And IO HDF5 2D output is done every 2048 steps. Generally speaking, IO is going to slow you down because not only are you writing to disk, which is slower than your CPU, but you're competing in bandwidth to the disk with everybody else who's on the machine. So you want to make sure that you don't do more output than you need. All right, let's see. That's entirely enough talking about that. Hopefully, I'm getting close to the end of my simulation. Are there questions? Yes, in the back. Okay, so time levels are, I have a value of a quantity now, and I have a snapshot of a quantity one time step in the past, and maybe a snapshot of the time before then. And depending on how I've set things up, I might need those time levels, say, to do interpolation in time. So I think we ask for like a certain order of interpolation in time. We need a certain number of time levels to do that. So there's lots of different reasons why you need multiple time levels for things. But that's one example of them. Yeah, and method of lines sometimes needs them and so on. Yeah, I suppose it's mathematically true that in principle, all you need from a mathematical standpoint is the initial data and how to get from one step to the other. But the reality is when you try to come up with a numerical scheme to get from one step to the other, sometimes you wind up needing multiple time levels to make that scheme work. I mean, you're right. From a strict mathematical point of view, that's true. But if I tried to, if think about this, if I tried to do the Euler method, which is definitely not going to need any past time levels, right? And if I'm not subcycling in time, then I probably don't need it for that either. But Euler is going to be unstable, so it winds out that for reasons of numerics instead of reasons of math, you need these other levels. Yes. Could I repeat the code again? You mean show the power file?
Yeah.
Oh, the vampire. Yeah, it should be in the chat. Withered Vampire 2. It should be in the chat. Yeah, the capital W and a capital V. The Withered Vampire 2. Yeah. Ah, good. It looks like I'm done. I hit time limit. See, I talked for just the right amount of time. How do I do it? All right. And then I list simulations, and it lists them as finished, both finished. If I had wanted to cancel the job, I could have done it with the stop command, but I didn't, and it's commented out anyway. If I wanted to delete everything I did, I could purge it, which I don't want to do because I want to analyze it. This is going to show me the output directory. That's where SimFactory put all my files. That's the naming convention it uses. So it's got, simulations directory where it puts all the simulations. It's got TOVET, which is the name of my simulation, and then output 0000. So potentially I can have more output directories if I restart from checkpoint and continue. We have some code we use to, that's exciting. What the heck? That's just wrong. Let's get rid of the bash thing in the front. So I know that I ran through this notebook multiple times and executed every step. And still something like that can happen. It's just kind of amazing to me. I don't understand how, but anyway. Bash and %bash and %pip are not compatible. Okay, so now what we have is we have a function to plot our time series using Quibit, which is the package that comes with the Einstein toolkit for doing graphics. And this is going to, it's going to pull out all our data from the files that we've generated and plot it. So that's what I got for my trouble. And here is a density profile, which you can see my TOV star sitting in the center of my grid there in the 1 octant. Now, this is 2 versions of the code.
sorry, something looks a little unfamiliar to me. All right, so I'm having, so this is the pressure and the cold pressure. And there is a fully symmetric view of my data where I have the reflection symmetry undo is performed. And then I'm finally going to compare. I'm going to compare my simulation with pre-recorded data. So the pre-recorded data, the stored values are in blue, and it shows you how the thing continues. The central density, our results comes from our actual simulation, and it's actually more reliable because the stored values were stored at low precision. And so that shows you how well the central density did against the expected answer. And as you can see, it's almost indistinguishable. And this is a way of turning the data we got into a compressed data format similar to the one that was used to store the values. So that takes us through how to download, compile, and run the Einstein toolkit for a basic TOV star, and to do some rudimentary visualization of the results. And I think I'm way ahead of time, but I'm done. Any questions? What's your error? I can't hear you.
It says that the
Sim factory doesn't exist.
I don't know where it's put that. Mine crashed too. Mine said cancel this time.
No, that's not crashing.
I know.
That's expected.
It didn't. The plotting stuff didn't work out.
Okay, I'd have to look at each of those things.
Mine says Sim Factory, Vincent.
Okay, so you need to go back to the top. Something went wrong with your checkout process at the beginning. Well, I don't know. I guess I can come over there and look at particular details, and I can do that in a minute or two if we have no general questions, because we have time. I can try and figure that out. Yes.
In general, when being started on a cluster,
Well, you would start at the top of this file with the instructions it has there. A lot of those files are Mac specific because Mac is the nightmare of this thing. But you just follow the basic instructions for the particular build that you're using, Ubuntu or whatever, and you will run into trouble, right? Because yeah, you know, the Python version is 2.8, or you know, they've got an old MPI or an MPI that isn't linked properly or something like that. There's always, sometimes I think I spend half my life figuring out how to compile things.
I get that.
And that's just life. And you know, what's one of the things Sim Factory is trying to do is trying to make you spend a slightly smaller percentage of your life compiling things.
Well, is that where you got gray hair from?
I'm sure it's not, but
I think there was a question in the chat. I don't have to.
can somebody what's the question from the chat?
Would you recommend users familiarize themselves with Quibit for reading data into Python for more modifiable plots, or would you recommend reading the ASCII binary files yourself?
Generally speaking, we recommend using Quibit, but sometimes it's valuable to just understand the ASCII files at some degree. Just take a look at them once or something like that, because it's, you know, if you're going to drive a car all the time, it might make sense to learn how to change the oil, even if you're going to normally get it done for you. But yeah, generally I would say use Quibit.
Any other questions? Anybody online? Okay, I guess that's a wrap. And I can sit with people who are having specific problems if you like. Okay, well, we can take a look at that. I keep expecting to hear recording stopped. Brandon?
You had some questions, I guess.
Yeah, yeah.